Hello, geometry students. In this lesson, we're going to take a look at our 9.4 through 9.6 notes. We're going to talk about compositions of transformations. We're going to talk about symmetry and also dilations. So let's start with a term that you may not have seen before. It's the word isometry. And isometry is a transformation that results in an image. Oh, we have a typo here. If you could change this. It's not supposed to say that. It's supposed to say that. Okay, so an isometry is a transformation that results in an image that is congruent to the pre-image. So congruent to the pre-image. And isometry is what we call a rigid motion. Okay, because since the pre-image is congruent to the image, that means it's rigid. It doesn't change its shape. It doesn't change its size. So let's circle the following transformations that would be isometries. Well, we should circle a reflection, a translation, and a rotation because all of those transformations result in an image that is congruent to the pre-image. However, a dilation either enlarges or reduces an image, so we shouldn't circle that. A dilation is not an isometry. Okay, so now let's talk about composition of transformations. So a composition of transformations is when a transformation is applied to a figure and then immediately another transformation is applied to its image. So we're going to look at a couple of compositions of transformations. The first one we're going to look at is called a glide reflection. And a glide reflection is a composition of a translation followed by a reflection. Now, if there's going to be a reflection, there's going to be a line of reflection. So a reflection in a line that's parallel to the translation vector. So I like this example here. Let's take a look at all these images. Let's number the images. Let's call this footprint number 1. This is number 2, number 3, number 4, and number 5. Okay, so as we look at these these transformations, as we look at number 1 to 2, you can see that the footprint has just, we just slide it, we just translate it according to this vector W. So translation number 1 to number 2 is a translation, and it's a translation determined by the vector W. Okay, then as we look at number 2 to number 3, well, that's a reflection, and it's going to be a reflection in the line L, and you'll notice that L is parallel to the translation vector. So translation number 2 to number 3 is a reflection, all right? And then as we look at translation 3 to 4, that's another translation determined by the vector W again. So number 3 to number 4 is another translation. And then finally, as we look at transformation 4 to 5, that's a reflection again in the line L. And notice again that L is parallel to the translation vector. So number 4 to number 5 is another reflection in the line L. Okay, so that would be a glide reflection just freehand. Now let's take a look at a glide reflection in the coordinate plane. So this next example says triangle JKL has vertices J, K, and L, which are given here. We're going to graph that triangle and its image after first a translation according to the vector Z0, 4, and then a reflection in the y-axis. So let's start this example by graphing these 3 points. Let's graph J, K, and L. So J is at positive 6, negative 1. So 1, 2, 3, 4, 5. Okay, there's J. And then vertex K is at 10, 2. So 1, 2, let's see, this is 6, 7, 8, 9, 10. Negative 2, 10, negative 2 rather. So there's K. And then L is at 5, negative 3. 1, 2, 3. So there's L. I'm going to move the names of my vertices so they're not going to be on the insides of the triangle. So this is J and this is K. Okay, so our first transformation is going to be a translation along the vector 0, 4. So what that means is, if we look at the coordinates of the coordinates of each vertex, that means that those coordinates x, y will be translated by, well, nothing, since the x component of this vector is 0, that means there'll be no change to x. But since the y value is positive 4, that means the y values will all be 4 bigger. So let's start with point J, whose coordinates are 6, -1. And when we translate it along this vector, when we keep the x value but increase the y value by 4, then J prime will be, oops, let me write that so you can actually read it. Okay, J prime will be the point 6, let's see, -1 plus 4 is 3, okay? J is at 10, 2, so that would be right. I mean, not K, well, first of all, let me go back. This is not J, it's J prime. This point is K prime. And then L prime would be at 5, 1, L prime. Okay, so you can see how our first transformation of translating along the vector 0, 4, just took this triangle JKL and shifted it up 4 units. So then the next reflection, we're going to follow that reflection. The next transformation is a reflection in the y-axis. So let's recall that the rule for a reflection in the y-axis means that we take xy and it becomes, if you're going to flip an image over the y-axis, it would have an opposite x value but the same y value. So that means that J double prime, remember J prime was 6, 3. Now we're going to apply this rule to J prime. So we'll take the opposite x value. So J prime becomes J double prime with coordinates -6, 3. Okay, and then K double prime would have coordinates -10, 2. And then L prime, double prime, would have coordinates -5, 1. So let's go ahead and graph those points. So -6, 3, 1, 2, 3, 4, 5, 6, 1, 2, 3. There's J prime, and then J double prime, and then K double prime is at -10, 2. 6, 7, 8, 9, 10, 1. So there's K double prime, and then L double prime is at -5, 1. There's L double prime. Okay, so we can see that we have done this composition of transformations. We did a translation followed by a reflection, and the result is J double prime, K double prime, L double prime. So a translation and then a reflection. Okay, now you'll notice that the result, our final image, J double prime, K double prime, L double prime, is the same shape and the same size as the pre-image was. So in other words, if we do a composition of 2 transformations that are isometries, then the result is going to be an isometry. So the composition of 2 or more isometries will also be an isometry. So it doesn't matter how many compositions that you do, transformations that you do in a row. Oh, I spelled isometry wrong. Let me fix that. How many transformations you do in a row, if they're all isometries, then the result is going to be an isometry. Okay, so the next composition of transformations we're going to look at is a composition of 2 reflections. Now, every time you do a reflection, there's going to be a line of reflection. So if we do a composition of 2 reflections, that means there's going to be 2 lines of reflection, and those 2 lines can either be parallel or they could be intersecting. So let's look at the 2 cases, starting with a composition of 2 reflections in 2 parallel lines. Well, okay, so here's an example of a triangle that has been reflected in the line K to result with this triangle, and then we take that triangle and reflect it in the line L, and so you can see that the result, this final image, we could get the same result if we would take this original triangle and just translate it. So in other words, a reflection in 2 parallel lines can be described by a translation vector. Now, that translation vector since these are the lines of the reflection and we're going to translate this way, then that translation vector is going to be perpendicular to the two lines of reflection, and it's also going to be twice the distance between the two lines. Okay, so in other words, if we reflect in two parallel lines, if we take a figure and reflect it over one of two parallel lines and then reflect it over the second line, that's going to be the same as a translation determined by a vector that's twice the distance between the two lines. Okay, we'll look at an example of that in just a minute, but let's look at the other case of a composition of two reflections. This time, the two lines of reflection are going to be intersecting. They're going to intersect at this point P. So if we take this line segment, if we reflect it in the line K and end up with this green line segment and then reflect that segment in line L, okay, that would be the same thing as taking our line segment and rotating it, okay? So two reflections in two intersecting lines can be described by a single rotation. Now, that rotation will be about the point where the lines intersect. So you can see how the two lines of reflection intersect at point P, and that's what we're reflecting this blue line segment about. And then secondly, we will reflect through an angle that is twice the measure of the acute or right angle formed by those two lines of reflection. So these two lines of reflection intersect, they form this angle X, okay? The angle of rotation then is going to be 2 times X. So let's take a look at a couple of examples. So let's take a look at example A. We're going to take this quadrilateral and we're going to reflect it in two parallel lines. So we'll reflect it in line M first and then we'll reflect it in line P. Now we're going to do this freehand, so it's not going to be perfect, but let's try our first reflection in line M. And it would look something like that. That's not too bad. So if this is the point A, then this would be the point A prime. Okay, so now we're going to take this image and we're going to reflect it in the line P. So again, we're going to try to do this freehand, so not going to be perfect, but give it our best shot. Okay, that's not too bad. So this point A prime becomes A double prime right here. So let's go ahead and label that. Okay, so now if we had a piece of patty paper, we could trace this, and you could do this if you want, but you could trace this quadrilateral, and doing this reflection in M and then a second reflection in P would be the same result as tracing this shape and then just sliding it to the right. So this reflection in two parallel lines is the same as a single translation, and so that's the same as a single translation to the right. And then how far would we slide it? We'd slide it straight to the right, and we would slide it double the distance from M to P. So let's take 1.75 and double that, and we would get 3.5 centimeters. Okay, so that single reflection in two parallel lines is the same thing as a translation to the right, 3.5 centimeters. And then our next example, we're going to take this triangle, and this time we're going to do a composition of two reflections, but this time the lines of reflection will be intersecting lines. Let's go ahead and give this point where they intersect, let's give it a name. Let's call it capital P. So actually I'm not going to put the P, I'm going to move the P. Let's put the P right here. Okay, so now what we're going to do is we're going to draw this by hand, so it's not going to be perfect, but we're going to first reflect this triangle in line M. So I'm going to stop the tape and do that. You might want to do the same. Okay, so here's our first reflection. We've taken this triangle and we reflected it in the line M. So this point A becomes A prime. Now we're going to take this triangle and we're going to reflect it in the line P. So again, I'm going to stop the tape because it might take me a couple of tries to do that. Okay, so this is a fairly decent reflection. So we first reflected our triangle in the line M, and then we reflected it again in the line P. So this point's name then would be A double prime. Okay, so again, if you had a piece of patty paper, you could trace this, you could trace this triangle, trace this triangle and rotate it double this amount, double 60 degrees. So this double reflection is the same thing as a single rotation of 120 degrees about point P. So let's write that down, what this, it says describe a single rotation. So that single rotation would be the same thing as 120 degree rotation, and then of course that would be counterclockwise. So we don't need to write that down, about the point P, because it will always be a rotation about the point where the two lines of reflection intersect. Okay, so now let's go ahead and turn our attention to a different topic. Let's talk about symmetry, and we're going to be talking about two different kinds of symmetry. The first type of symmetry we're going to talk about is what's called reflectional symmetry, and reflectional symmetry can also be called line symmetry, okay? Because what that means is that we can, if a figure has reflectional symmetry, that means that we can draw a line of reflection like on this figure, and the figure can be mapped onto itself by a reflection in the line. So in other words, if I were to if you were to take your paper and fold it right along this line of reflection, then the left side of this crab would lay right on the right side. Take a look at this starfish. This starfish has 5 lines of reflection. If you fold your paper along any one of these lines of reflection, then the one side of the starfish would match up to the other side. Now letter C, I think I changed your notes. I think you have a picture of a duck on your notes, but I think this was a seashell, I guess. But no matter what, if you look at your example or this example, there is no line I could draw where the left side would match the right side or the top would match the bottom. So let's go back and just summarize. The first figure has 1 line of symmetry. The second one has 5 lines of symmetry, and the third example has no lines of symmetry. Okay, so what about these geometrical figures? Take a look at this parallelogram. So you might think that the diagonals would be lines of symmetry, but I would challenge you to trace this, and maybe we'll do this in class, but trace this parallelogram, fold it along the line of symmetry, and I think you'll see that the one side actually does not line up with the other side. So this has no lines of symmetry, okay? Letter B has 1 line of symmetry. It would be this vertical line, okay? So 1 line of symmetry, okay? And then letter C has 2 lines of symmetry. There'd be a vertical line of symmetry, and there'd be a horizontal line of symmetry. And again, you might be tempted to think that the diagonals are lines of symmetry, but if you were to draw a diagonal and fold along that diagonal, you would see that one side does not match up with the other. So this one has, 2 lines of symmetry. Okay, so that would be reflectional symmetry. That means that you can draw a line of symmetry. The second type of symmetry we're going to talk about is called rotational symmetry. Sometimes it's called radial symmetry. What that means is, it means that the figure can be mapped onto itself by a rotation between 0 degrees and 360 degrees about the center of rotation. Okay, so we'll do this in just a second. The number of times a figure maps onto itself in 360 degrees is called the order of, order of symmetry, and the magnitude of symmetry, or also called the angle of rotation, is the smallest angle through which a figure can be rotated so that the figure maps onto itself. Okay, so let's take a look at this example that says state whether the figure has rotational symmetry, and then if it does, state the order, which is how many times it would map onto itself in a 360-degree rotation, and also the magnitude of symmetry. That would be how many degrees you'd rotate the figure until it maps onto itself. So we'll do this in class with some patty paper, but if we were to trace this regular pentagon and we started rotating it in the counterclockwise direction, we would find that it maps onto itself a total of 5 times. So yes, this does have rotational symmetry. The order, I'm sorry, this isn't a pentagon, it's a hexagon, duh. So that means it's going to map onto itself 6 times, not 5 times. So the order would be 6, okay? And then the magnitude, if you take 360 and divide it by 6, that means it's going to map onto itself every 60 degrees, okay? The second figure, this right triangle, if we were to rotate this about the center of rotation, we would have to rotate it the entire 360 degrees before it would map onto itself. So if it takes and remember the definition said it has to map onto itself between 0 and 360. So if you have to rotate the whole 360 degrees in order for it to map onto itself, then this has no rotational symmetry. The third example, if you were to rotate this, once you get the figure turned upside down, it would map onto itself. So yes, this does have rotational symmetry. The order would be 2. It would map onto itself twice in a 360-degree rotation. So that means that the magnitude is 180 degrees. Okay? Now let's talk about symmetry of 3-dimensional figures, okay? Symmetry of 3-dimensional figures, there's 2 types. There's plane symmetry and there's axis symmetry. Okay, plane symmetry means that the figure can be mapped onto itself by a reflection in a plane. When we're in 2 dimensions, we reflect an image in a line, but in 3 dimensions, we reflect an image in a plane. So if you look at this prism here, this has plane symmetry because this green plane slices this 3-dimensional figure into 2 pieces that match each other. We could map this onto this. We could also draw a horizontal plane of symmetry that would chop this 3-dimensional figure into 2 pieces where the top would be a reflection of the bottom, okay? So that's plane symmetry. The other type of 3-dimensional symmetry is called axis symmetry. That means that the figure can be mapped onto itself by a rotation between 0 and 360 degrees in a line called the axis of symmetry. Axis of symmetry. So you can see how this cone has an axis of symmetry. If we start to rotate about that axis, this cone would be constantly mapping onto itself. Okay, so a couple of examples. The examples say, state whether the figure has plane symmetry, axis symmetry, or both. Okay, so this L-shaped prism doesn't have any axis symmetry. However, we could, and I don't even think I can begin to draw it, but we could slice this thing vertically, and the front would be a reflection of the back. So this figure does have plane symmetry, but it has plane symmetry only. It does not have rotational symmetry. Okay, this figure, that's a regular pentagonal prism, has both. We could slice this thing down the middle, or we could slice it horizontally with a plane that would be where the one side would be a reflection of the other side. So it does have plane symmetry. It also has rotational symmetry. If we had here's the center and the center. If we had a line that goes through the center and we started rotating this, it would map onto itself 3 times. So this figure has both. It has plane symmetry and it has rotational symmetry. All right. Oh, that's. Okay, the last transformation we're going to look at today are dilations. Dilations. Okay, so a dilation with center C and a positive scale factor K, where K is not equal to 1, because of course if K were equal to 1, you wouldn't have an enlargement or a reduction. So a dilation with the center C and positive scale factor K is a function that maps a point P onto its image such that if P and C, remember C is the center of the dilation, if P and C coincide, then the pre-image and the image are actually the same point, okay? But if P is not the center of dilation, then P lies on, oops, there's an extra bullet point here. Can you mark that out? That shouldn't be there. Okay, so let's start this over. If P is on the center of dilation, then P lies on ray CP, and the distance from C to P prime is equal to the scale factor times the distance from C to P. So that's really wordy, so let's take a look at an example. Here we have a triangle LMP that's being dilated under a scale factor of 2.5, and here's our center of rotation, okay? So that means that L prime lies on this ray, CL, in such a way that the distance from C to L prime is 2.5 the distance from C to L. Look at point M prime. It lies on ray CM, and the distance from C to M prime is 2.5 times the distance from C to M. And then one more time, take a look at P prime. P prime lies on ray CP, and the distance from C to P prime is 2.5 times the distance from C to P. So let's try our hand at doing a dilation by hand. So this example says we have triangle ABC and center rotation D. Okay, if you have a ruler, grab one to draw the image of triangle ABC under a dilation with the center D and a scale factor of 1/2. So the first thing you might want to do, if the scale factor is 1/2, that means that the image is going to be closer to the center of rotation. Well, in other words, it's going to be between the center of rotation and the image. Unlike here, we had a scale factor bigger than 1, so your image was farther away. It was on the other side of the image. Here, if your scale factor is less than 1, it's going to be here. So let's start by doing this. Let's just connect C to B. Center of rotation to B, center of rotation to A, and the center of rotation to D. Again, if you have a ruler, it'd be a good time to use it. So where am I going to? Let's start with point wherever I would place B prime. Well, if my scale factor is 1/2, then I need to place B prime about here, because the distance from D to B prime needs to be 1/2 the distance from D to B. So let's put it right about here, okay? And then I'm going to put A prime, half of the distance from D to A, so let's just note that D to B prime is 1/2 the distance from D to B. D to A prime is 1/2 the distance from D to A, and D to C prime is 1/2 the distance from D to C. Okay? You'll also recall from our previous discussions of dilations that if your scale factor is greater than 1, then the dilation is going to be an enlargement. And if the scale factor is between 0 and 1, then that scale factor, that dilation, will be a reduction. Okay, so we've used the definition to do a freehand dilation. Now let's talk about dilations in the coordinate plane. So to find the coordinates of an image after a dilation centered at the origin, multiply the x and y coordinates of each point on the pre-image by the scale factor of the dilation, which is k. So in other words, if we're going to take this line segment and we're going to dilate it with the center of dilation at the origin, if the scale factor is 2, then we would just take these coordinates 2, 3, and we would multiply each coordinate by 2. So it becomes 4, 6. So if your scale factor is k, then if you're centered at the origin, the dilation xy under that dilation would become kx, ky. So let's take a look at an example. It says graph the image of each polygon with the given vertices after a dilation at the indicated center with the given scale factor. So this time, notice here are it's a quadrilateral. We're going to plot those points in just a second. Our center of location, though, is not at the origin this time. It's at 1, 1. So what we'll do is we'll kind of pretend like 1, 1 is the origin. You'll see that in just a second. And our scale factor is 2. So let's start by plotting the 4 points. I'm going to pause the video and do that. So you can see I've plotted B, C, D, and E. I've also plotted the center of rotation, and I've given it a name P. Now, I want you to notice that P is not at the origin. So what we're going to do is we're going to just kind of pretend like P were the origin. And if P were the origin, then this point B would have coordinates -2, -2. So if this were the origin, then B would have coordinates -2, -2. And if I'm going to dilate under a scale factor, under a dilation with a scale factor of 2, that means I would double that. So if these points were -2, -2, then I would double that. I'm going to plot -4, -4. So I'm going to go ahead and pretend like P is the origin, and I would plot the point -4, -4 from here. So I'm going to go to the left 1, 2, 3, 4, and down 1, 2, 3, 4. So B prime would land right here. So here's B prime. Now, what I want you to notice is if we were to draw a ray from P to B through B prime, you can see that B prime lies on ray PB, and the distance from P to B prime is twice the distance from P to B. So let's do the same thing with C. Now, let's pretend like this were the origin. If it were, then the coordinates of C would be -1, 2, 3, 4, 5, and then down 1, 2. So -5, -2 would be the coordinates of C if this were the origin. So let's take -5, -2 and double that, so that would be -10, -4. So from here, I'm going to go to the left, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then down 1, 2, 3, 4. And there's my point C prime. Okay, and again, you can see that if we were to connect the dots, then C prime lies on ray PC, and the distance from PC prime is twice the distance from PC. So now let's do the same thing with D. If I'm pretending like this is the origin, the coordinates of D would be 1, 2, 3, 4, 5, 1, 2, 3, 4. So it'd be -5, -4. So I'm going to double that, -10, -4. So D prime, well, hold on. I'm sorry, it'd be -10, -8. So from our fake origin here, we would go to the left 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 units, and then down 1, 2, 3, 4, 5, 6, 7, 8. So D prime is right here. Oops, wrong color. D prime is right here, okay? And again, you can see that D prime would lie on ray PD, and the distance from P to D prime is twice the distance from P to D. So let's do the same thing with E. Let's pretend like this were the origin. Then the coordinates of E would be -2, -1, 2, 3, 4. So let's double that and go -4 and then -8 down to here. So E prime, oops, wrong color. And wrong pen. Oh, okay, there we go. E prime would be right here, okay? And again, if I draw a ray PE and then keep going, we can see that E prime lies on ray PE, and the distance from P to E prime is twice the distance from P to E. So let's go ahead and draw our image. And so we can see that C prime, D prime, E prime, I guess I should start with B. B prime, oh, I missed. Oh, what did I do? I'm so sorry. Let me fix this. I think I counted wrong. Let's see. Yes, I counted wrong. Let me see if I can fix this. Okay. Hold on, I got to do a little repair work here. Okay, so I counted wrong. For E prime, Let me erase this because I have it in the wrong spot. So sorry about this. Let's get E prime in the right spot. Okay, so from, let's see, if the coordinates of, if this were a fake origin, then the coordinates of E would be -2, -4. So E prime would be 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. E prime would be right there. I bet you guys thought I was crazy. So let me put E prime in the right spot, and let me redraw that ray. There we go. That looks better. So now, E prime does lie on ray PE, and the distance from P to E prime is twice the distance from P to E. So finally, let's finish drawing our image. There we go. That looks much better. So we can see the reflection of our image point, our pre-image B, C, D, E. It has reflected under a dilation centered at point P with a scale factor of 2. Okay, so this is not your homework. Your homework is going to be a worksheet that we'll work on in class, and I will see you then.